Hello? Hello, dear viewers. So, recently I was a participant of 46th Petrozavodsk training camp, and we actually managed to solve almost all problems. So this problem I is the last one. I chanced to already skim through the editorial, but it was like fast and I didn't look really into details. So starting from this point, I'll try to do it as much as possible on my own and upsolve it. So what's the problem about? We have a table n by m matrix, and we know maximum in each row and in each column. So these numbers are known, each of them is known. The goal is to calculate the number of such matrices, given that all numbers are non-negative integers, I believe. Non-negative integers, yeah? Positive integers. It's actually positive integers. Okay. So I have already captured several ideas from the editorial. So first of all, let's sort all maxima and minima, for example, in increasing order. So we know maximum A1 is at most maximum A2 is at most maximum AN, and the same for B1, B2, and BM. Actually, let's also read these numbers. So to read them, we need to turn on files. And turn on multitest. Yeah, actually there is no multitest here, however we will turn it on. Sorry. We will turn it on in order to simplify our testing. So we're gonna say int t equals 29. If not solve tests, return, and here bool solve test. We have int n and m. If we fail to read n and m, we return false, else we return true, but before that we read the arrays. Actually, we can do it like this. Well, and then we print the answer. Finally, what we really need to do is to create modulus and sort the arrays. Let's think what's next. So after the sorting, it shouldn't be the hardest task. So the editorial stated the following. Let's try and say that instead of maximum being exactly a1, it should be at most a1. Or yeah, it's at most a1. But then, actually the answer is easier. So if for each row and each column we say that the maximum is at most this number. For example, what is the number of ways to choose this number? Yeah? It should be at most a1 and it should be at most bk, where k is the number of column of this entry. So there are minimum of a1 and bk ways to choose it. So actually the answer is product of all minima among all I from 1 to n and j from 1 to m. And this can be calculated easily. For example, if we consider 2 pointers or anything like this. Even not 2 pointers, just sort both arrays simultaneously into one big array. And if we consider all these numbers, it's easy to calculate this product. The problem is we don't need it. We don't need the condition that the maximum is at most AI. It should be exactly AI and exactly BI. Yes? Yes. Well, the probability is 0. So it's recommended then to consider exclusion inclusion principle. So what is recommended in exclusion inclusion principle? So how can the maximum be exactly AI? This means that actually maximum is at most AI, but maximum is not at most AI minus 1. So this is true. Yeah, and this means that let's consider n plus m conditions. So first of all, let's consider some ground conditions. Ground conditions that AI maximum in row I is at most AI and maximum in column I is at most BI. So these are ground conditions and they are product of like minima, which I said. this number of ways to satisfy these ground conditions. Yeah, let's introduce n plus m more conditions where AI says that maximum of Ri is at most AI minus 1, and also m conditions bj such that maximum in column j is at most bj minus 1. So what we need in our answer is the fact that none of these n plus m conditions are true. Let's call them like Ci. So we want none of these Ci's to be true. Actually, to calculate the intersection of several sets, we can apply inclusion-exclusion principle and say that instead of that, let's try to satisfy some of them. To satisfy exactly K, for example. So let's consider all subsets of our conditions, and we satisfy exactly we satisfy these D conditions, but we don't say anything about satisfying anything else. In this case, if we multiply it by minus 1 to the power of D, then actually we will get the answer. For instance, they simply say, let's this be the ground area. For example, let this be some condition A, which we don't want to hold, and this is condition B, which we also don't want to hold. We want to calculate this area, not holding of any of these conditions. Instead, what is proposed is to calculate everything with sign plus. But then we calculate exactly one condition with sign minus. Then we calculate another one with also sign minus. And see how these cancelled out, but this is with sign minus because we added it once but subtracted it twice. However, there is one more term in this sum, which is D equals C, in this case A plus B. And minus 1 will be to the power 2, so it will be positive. And we add it back. So actually, we will consider once exactly this outer area. So exclusion-inclusion principle will guarantee that we calculate our answer. The nice thing is that these conditions which we chose, they are also of type that some maximum is at most number. And the fact that some maximum is at most number simply can be rephrased as this number is that each number matrix ij is at most this number. That's it. You don't need anything else. So that's it actually. However, if we simply apply this formula, we will get 2 to power n plus m time, and maybe times n times m. Okay, times n plus m if I'm accurate with that. I can get something like this, and unfortunately it is slow, so I don't want my algorithm to work that long. Instead, let's think of something else. However, I believe I will need some stress solution. So let's actually prepare ourselves for stress. Which is far from ideal, but let's do it. Far from ideal because I don't really want to write stress in this problem. But what can I do? So let's start with creating test, which is pair vi generate test. So we need some randomness. Also, I would like to include Chrono, just in case. And we will surround our solve test with Chrono. Okay, here we create static random number generator. Also, let's include the number n. And let's only create small tests so we can actually look at this rectangular matrix. Well, here n equals UID 1n of RNG, same for m. Let's create VVI matrix NVI m. I will only create tests for which the answer exists, because otherwise it will always be 0 for this number, and I don't really like it. Then let's create this was a bad idea to call it M, let's call it C, for example. Let's fill it with random numbers. So Cij equals, so let's also call auto entry equals UID of 1C. Here we call entry of RNG. Then let's fill the array A and B. And actually we can fill it here. So we actually don't need C. Here we can say that we simply have in C equals this entry and AI equals max of AI and C. And sorry. And Bj is equal to maximum of Bj and C. Finally, we we return A and B. So this is generate tests. Then let's make a slow solution. Where we simply calculate the answer with inclusion-exclusion principle. Actually, I can do it in NM time, I don't care. So let's simply consider all masks. So for int I equals 0, I less than 1 to the power of a dot size plus b dot size. Maybe even I don't need this. So the I is the mask. Now let's actually let's call it M since it is the mask. Mask, mask, mask. Here we go through all. Let's calculate the answer, current answer. Yeah, and then what? Let's also make the function which calculates pop count, which is not really hard. So while n, if n and 1 so like int ans equals 0, ans plus equals n and 1, and divided by 1, and return ans. So if pop count of mask is odd, we need to subtract it from the answer. Else we need to add it to the answer. And then return answer. Let's write the functions diff and add. Sum and diff. Nice. So here we will calculate the answer. To do that, we go through all elements. Let's actually call n and m. So here we say that current answer. Let's actually calculate, first of all, row maximum and column maximum. So int row maximum equals like AI. But if mask contains bit I, we subtract row max 1 from row max. The same for column max. If mask contains bit of 1 over j plus n, we subtract column max. So in the end we can say that current ans equals product of current ans and minimum of row max and column max. And so we need to write the function product, which is again very easy. So return ll A times B percent M. And using LL equals int 64T. Well, we are done here. So actually we can try to say that we return find and slow of A and B. Let's try and do it. So let's copy the samples. We remove it, and it. Let's see what it says. It of course says that we have some compilation errors. And this is because it wanted this definition somewhere higher. However, we don't need the definition to be high. We only need the declaration to be high. And we can do it like this. So 89, it actually seems really strange. Because I needed to remove 0. It takes a lot of time on this test, I think. However, it still should take some reasonable time, because 2 to the power 25 times okay, 89, 0. Yeah, totally correct answers. So far, 100% correct. Actually, let's add this output to... Okay, I don't care. Let it be like this. So, this function is not lying, it is working slow. Now we don't want to use it here. Instead, we would like to have some faster approach. To do that, we need to eliminate our exclusion-inclusion principle, because it takes exponential time, of course. So let's think. First of all, let's consider, for example, one column. Assume that we already chose some numbers here, so we know that the maximum is at most, for example, A1, A2, etc., AN. It is at most these numbers, but not exactly these numbers. Can we eliminate... Then I want to state that actually now all columns are independent. We can solve the problem separately for each column. If we have fixed these numbers, we can work it out independently for each column. Let's do it. So we take one column, and actually we know that we need here at most A1, but at least be at most maximum of A1 and BK minimum. So the number here should be at most A1 and BK. Well, actually, what I want to say is I really don't need exclusion-inclusion principle for all columns to them power, because if I do it independently, I just calculate the answer. So let's call f of some fk of b equals product from I equals 1 to n minimum of ai and b. Yeah, then I actually just need to find the product of from j equals 1 to m of f b j. No, actually, why k? I don't need k here, I simply need f. F of bj minus f of bj minus 1. So this is the answer. This is simply the answer. Okay, the problem with that is it's still slow. It's still slow because I still need to make the exclusion-inclusion principle on the rows. Yes, I eliminated the exclusion-inclusion principle for columns. Because, again, why it's slow? It's slow because I need to consider all subsets of my conditions. But actually, sometimes they are independent. So for example, I have some ground, I have some condition D, yeah, and I have some condition E. And sometimes it's true that G times DE is same as D times E. This is called independency of these two actions. Not actions, events. And if these two events are independent, it can also be reformulated as probabilities. So d divided by g times e divided by g is dE divided by g. And this means that these two events are independent. So their probabilities, their product is equal to the probability of their intersection. And we have it here because what happens in some column does not affect the other columns conditionally that we have fixed numbers AIs. However, we don't fix them in the end. In the end, we need to iterate over all possible combinations of power 2 to the power n. Which is sad, but let's think. Let's continue thinking. So again, we want to... So for fixed numbers a1, etc. an, the answer is product of I equals 1 to n of product of j equals 1 to m not product but difference of two products. So I try b j. No, I iterate over all columns first of all. I iterate over all columns and I try to subtract the answer for bj and bj minus 1. So this is my answer. And in the end, okay, this is answer for at most some numbers AI. But the answer for exactly AI is also some for delta I in 0, 1 minus 1 to the power of sum of deltas times this thing, which is product from j equals 1 to m, product of I equals 1 to n minimum of ai minus delta I bj minus product of I equals 1 to n minimum of ai minus delta I bj minus 1. And we iterate over all possible delta i's to subtract them here and here. What do we do here? So, and delta i's where I are all numbers from 1 to n. So actually 2 to the power of n addends. So we don't want it to take to the power of n time. So we need to somehow shrink it down. Not the easiest thing to do. If you allow me my honesty. But maybe sometimes it can be simplified. If, for example, sometimes it is simply, it has a common multiplicand. When does it have a common multiplicand? It has it when ai minus delta I is at least bj. Why is that? This is because we can eliminate it from both products. If we can eliminate it from both products, then we can put it out of this product and actually after that we can put it from out of this product. So this is somehow simplified. Moreover, if ai minus delta I is at most bj minus 1, then actually it is simply bj and bj minus 1 here. So there are actually two types of numbers, when it is at least bj and which is when it is at most bj minus 1. And for the second case, it will be simply some power of this number minus some power of this number. Okay, let's try to rewrite it. So answer of AIs equals sum for all deltas. Then we consider What do we consider? Okay, let's write it as j equals 1 to m. And then it is kind of interesting because, so, first of all, each ai minus delta I, which is less than bj, which is at least bj, they are put here as a product. So let's say I from 1 to n, and ai minus delta I is at least bj. So for these things, we simply say ai minus delta I. Okay. Then we multiply it by bj to the power of the number of numbers which are at most bj minus 1, and minus bj minus 1 to this power. Okay. Okay, sounds legit. Okay, maybe we can fix some concrete number ai. Well, yeah, maybe we can. Maybe we can. Let's actually think of some number ai. Okay, let me rewrite it again as it was before. So product of I equals 1 to n, bj to the, or not bj to the power, a minimum of ai minus delta I minus not times, but what? Minus product minimum, here because I need bj, minus product of minimum ai minus delta I bj minus 1. Well, so let's take some fixed number ai. So there are several types of numbers bi. So we have ai. There are several types of numbers bi. So on the number line. So here is ai minus 1. So there are bi's which are here. So actually let's assume that they are in decreasing order. So here we have some b1 etc bk. Then we have bk plus 1 etc bl, bl plus 1 etc bs, and bs plus 1 etc bn, bm. So we have these numbers. Okay, numbers here are simply not considered in this minimum, because in this minimum the minimum is taken and it is either this or this number. Yeah, so what can we do then? We can, oh sorry, you can see my writings. So here I can take from I equals 2 to the power n and actually eliminate ai minus delta I here. But this is also only for these b's. Okay, what about these b's? For these b's, it's still true. It's still true, I think. Is it true? Maybe it's not true. Yeah, because when I take ai minus... yeah. We don't need to to discriminate between these two, because even if some bj is equal to ai, it's still true that ai is at most this bj and ai minus 1 is at most this bj. So actually, even for b which is equal to ai, it's still true that we can move it out of this product sign. Okay, however, there are also these numbers bk, b1, etc. bk. Let's call it actually. So here we have b1, etc. bk, and here we have bk plus 1, etc. bm. Yes, so if we do it, then we have sum of delta i's. So first of all, we have product from j equals 1 to k of something times product of j equals k plus 1 to m, and here we can move it this ai minus delta I here, and then let's call it 1, a1 minus delta 1, and then take product from I equals 2 to n, minimum of ai minus delta I bj minus product of minimum of ai minus delta I bj minus 1. Oops. However, there is also this part where this bk is at most ai minus 1. In this case, these two numbers are taken as minimum. And what can we do? In this case, we cannot do much. We simply say that it is a product from 1 to n, bj times minimum of... No, not like we can put bj here. So let's write like this. So we have bj times product from I equals 2 to n of this minimum. Yeah, then minus bj minus 1 times the same product. So ai minus delta I bj minus 1. Okay, actually, it's easier in this case because I can rewrite it like this. So here I have ai minus delta I to the power m minus j. Why is it nice? Because therefore I can remove it out of the summation sign here. Yeah, so I have, what do I have? I have delta, sum of delta 2, etc., delta n, then sum of delta 1, and then something hard to explain where I have, no, let's do it the other way. Yeah, the other way. First of all, sum of delta 1 from 0 to 1, then sum of delta 2, etc., delta n, then some function of delta 1, etc., delta n. Let's look at how this, what this function looks like. See, actually we don't, we are not dependent on delta 1 here, we are not dependent on delta 1 here, and we are not dependent on delta 1 here. We're only dependent on it here. But here, it's also quite simple. Yeah, because here we simply removed ai minus delta I to the power m minus j. So we can write it here. ai minus delta I to the power m minus j. And then it's simply function from delta 2 to delta n, because we are not dependent on delta 1. Yeah, so we simply need to, when we have this double summation, it's actually easy to rewrite it as sum of delta 1 from 0 to 1 of this thing times the sum of the everything else. Okay? Well, it's extraordinary. But here, this is simply the difference of two powers. So it's like equal to ai to aa1 to the power m minus j minus ai minus 1 to the power m minus j. And this can be calculated in logarithm time. Well, so we have removed one multiplicand from this sum, and we can repeat it. Yeah, for example, here again, so again, let's fix some bj. So let's fix bj. For fixed bj, we have product from 1 equal 1 to n, minimum of ai minus delta I bj minus the product of minimum ai minus delta I bj minus 1. This is for fixed bj. So for this fixed bj, if we have AI at least bj plus 1. So AI, if it is here, then it is the bj is the minimum. So we simply have we can write it here before the product sign. But if the number is bj or less, then ai minus delta I is always the minimum. And in this case, it can be fully eliminated out of this product and put here. So let's rewrite what we have in the end. First of all, for each number from y I equals 1 to n, we have ai to some power di minus ai minus ai minus 1 to the power of di. What is di? Di is simply number of bj's such that ai is at most bj. And this can be calculated with 2 pointers. Fine. But then we have the product of the residual thing. What is the residual thing? In the residual thing, we have product from j equals 1 to m, and we only are left with these powers. So bj to some power minus bj minus 1 to some power. What is this power? Let's call it ej, and ej is the number of ais which are at least bj plus 1. Well, does it work? Does it work? I'm afraid of this asymmetry, because here we have a non-strict inequality, but here we have the strict one. And I don't really like it. Yeah, let's make some sanity check. For example, we have 1 by 1 square, and here we have maximum equal 4, and here we have maximum equal 4. Then we have product from 1 to n, ai to the power of what? Of the number of di's which are strictly less number of di's which are at least ai, and this is 1. Okay, so this is simply 1. But then we multiply it by product of for all j's, and I believe that after the removal it might become sad. Yeah, it might simply become 1 minus 1. So this is what I don't like. That it becomes 1 minus 1. And this becomes 1 minus 1 because I have a product of n numbers and I simply removed one of them and I simply have 1 minus 1, don't I? Yeah, I do. Ah, I see where is the catch. The catch is in the numbers AI equal to BJ. So it's actually making our solution more difficult, but let's look at them. So again, we have I equals 1 to n, product of minimum of AI minus delta I bj minus product of minimum AI minus delta I bj minus 1. Okay, the smaller problem here is that if AI equal to bj is equal to bj, then it's unclear what to do here. It's unclear because, well, if we consider all four cases, so we cannot eliminate AI minus delta I. We can eliminate it from here, but we cannot eliminate it from here. So what to do? So let's think again. We have bj, some fixed bj. So if AI, and this is bj minus 1. So if AI is here, then it simply contributes in this power. If AI is here, or even here, I think, yeah, if it is here including bj minus 1, then I can write it like this and eliminate out of the sum completely, remove out of the sum completely. So the only problem is the numbers which are equal to bj. So let's assume that there are q numbers which are equal to q numbers AIs which are equal to bj. Let's write it like this. So I have A numbers here, B numbers here, and C numbers here. This is the easiest thing. So all these numbers are simply removed. I forget about them. They are written in the beginning or in the sum, as I said. This is simple. Then we have bj to the power c, and this consists of the numbers which are greater than bj. Finally, we have b numbers which are equal. So what do we have here? Actually, here we always have this number. I know. Note that we have a product. Yeah, we have a product. We have a product of a lot of things. Sorry. We have a... Again, sorry. We have a product of many things. Yeah? Let me write it again. We have a sum, actually. but inside this sum we have a product. So let's assume that we have AI equal bj, and let's assume that delta I equals 1. Note that what? Okay, let me rewrite it. So again, we have some. So first of all, we removed everything what we can. This is product from I equals 1 to n, AI to the power of the di minus AI minus 1 to the power di. Okay, we removed it. Then we sum over all di's. Then we consider product for all j's from 1 to n. Okay, yeah, I see. So, okay, if AI equals bj, then actually in this minimum we always take this number, and in this minimum we always take this number. So we can write that we have, so we have, first of all we have bj to the power cj times, well, okay, bj minus delta j to the power bj. Then we subtract bj minus 1 to the power cj times, actually bj minus 1 to the power bj. So actually cj plus bj we have. Okay. So here we have actually product of such things. So let's write it. Sum of delta i's, product of j from 1 to m of this thing. And it is independent among all j's. So we can swap the summation and product. So we have product from j equals 1 to m. And here we only sum over it's not independent. Unfortunately, it's not independent. However, I can also sum over bj's. So let's take some fixed value and let there be like qj numbers be not j, let's introduce other index k. qk numbers bj which are equal to k. Also let there be rk numbers ai equal to k, and there let there be sk numbers ai which are greater than k. Okay, let's then look at what we have. So here again we have p from 1 to n ai di minus ai minus 1 di times product for all k's. So let's look at one number bj which is equal to this number k. Then we have simply k to the power cj which is sk. Okay, for fixed k we can sum over all deltas. Sum for all deltas which there are k of them. So delta is from 0, 1 to the power rk. And note that afterwards I need to raise it to the power qk. So something to the power qk. What is to the power qk? So bj to the power sk times product of bj. Let's call it k instead of bj because we forget about bj actually. K minus delta I actually. And we don't need bj because these deltas are actually different. And minus bj minus k minus 1 to the power rk plus sk. Okay, let's think what we do here. So we product over all k's. Then we remove this k to the power sk from this summation. Then summation goes over all products of k minus delta I, which we will consider a bit later. Also, I forgot about power of minus 1 to the power of delta, I think. Did I forget about it? Yes, I forgot somewhere in the beginning about it. Oh my, I forgot about it. Okay, it is here. Okay, for example, here, what should happen? So it should be minus 1 to the power sum of deltas here. So okay, let's write it for this one. Then we subtract this number, and actually it will be minus k minus 1 to the power rk plus sk times 0 if rk is at least 1. So times rk is 0. And actually, so if we need rk to be 0, we can simply write it as k here. Okay. So rk should be 0. Or we don't subtract it. Let's continue. And here, what here? K to the power sk. And here minus 1 to the power sum of delta i's. Okay, let's think about it. So it can be rewritten as simply so again we can swap it because all these multiplicants are independent. So we have product over k, k to sk, then product from I equals 1 to rk, then sum of delta 1 from 0 to 1. And here we simply have k minus 1. No, let's remove it. K minus 1. And that's it. And it is simply 1. So we have simply k to the power sk minus k minus 1 to the power sk times rk equals 0. That's it. Okay, so the final formula seems like this. Product from I equals 1 to n a I minus and this is to the power qk. Yeah. ai to the power di minus ai minus 1 to the power di, where di is the number of bj's which are at least ai. Plus 1 times, now let's rewrite it again with bj's. So for each bj, this is simply iterated once, and we need to take here bj to the power of sj minus bj minus 1 to the power sj. What is rk? And times let's call it cj, and where sj is the number of AIs. So I can write it here as greater, and here I can also write it as greater. Yes, so AI is greater than BJ, and CJ is the fact that there does not exist such AI which is equal to BJ. Okay. Okay, let's consider some examples. So again, let's consider example 4 and 4. So I have here 4 to the power of 1. 4 to the power... Oh, this is again messed up because this multiplicand is 0 this time. But the answer is not 0. This is because I again failed in my formula. I again messed up. So now it becomes garbage. Okay, let's work it out. Again. So I have product. So first of all, I have sum over all delta i's from 0 to 1. Then I have product from j equals 1 to m. Then I have product from I equal 1 to n of minimum ai minus delta I bj minus product from I equal 1 to n minimum of ai minus delta I and bj minus 1. Okay, my issue seemingly was that when ai minus delta I is at most bj, so ai is less than bj, then I simply removed it here and this was correct. Removed it here and it still was correct. But then I couldn't remove it here because there were some other occurrences of ai minus delta I, so these two things were not independent. I actually wasn't able to remove it completely. Okay, let's rewrite it without violation of rules. So again, let's rewrite it without violation. So delta I from 0 to 1. Okay, first of all, I have product from I equal 1 to n, ai minus delta I, to the power of di. Again, di is the number of bj's which are at least ai plus 1. I can remove all of them out of this sum. After that, I can write product from j equals 1 to m. Okay, here I can remove bj here. What will it be? It will be bj to the power of, let's call it ej. So ej is the number of AIs such that AI is at least bj plus 1. Okay, what we have now in this product? In this product, we simply have AI minus delta I several times. So we only have equal numbers to... we have equal numbers. Yeah, we have equal numbers. Let's call them somehow. So let's call fj equals number of AIs such that AI equals bj. Then here we have like bj minus delta I, a product of this number. Bj minus delta I and here we have simply this number as a minimum. So we have bj minus 1. Again, if this number was at most bj minus 1, it was already removed here. So now we have simply bj minus 1 to the power ej plus fj. Okay, this is awful. Unfortunately, this is really awful and I don't like it. However, it clearly seems like I can remove it somewhere out of this scope. Can I? I think I can. Okay, let's do it. Can I do it? Okay, not really. I have this strange product. I unfortunately have this strange product. So my error was that I seemingly separated these two things. They said that now this works independently of this one. However, it was not the case because here we have delta I and here we also have delta I. We cannot separate them that easily. I would like to separate them easily, but I cannot. So how to separate them? I think it might be important that we have some structure. So here, I really don't know. So here I need to say that, I need to say that here we only consider such i's that ai equals to bj. Yeah, this is important because maybe this means that I can separate the variables. Okay, again, let's simplify it a bit. So here I have pi equals 1 to n ai minus delta I to di. But here, let's take the product over all case, or all case. And again, let's introduce those variables. So qk equals number of bj's equal to qk equal to k, sk equals to the number of aj's ais which are equal to k, and it is rk, and sk is the number of ais which are greater than k. So here we have something to the power qk, here we have k to the power sk times like product of something terrible actually. Product of a I of what? Let's call like rk equals the set of all I such that ai equals k. Then here we have I in rk. Here we have bj minus delta I minus bj minus 1 to the power rk plus sk. Okay, now it can be clearly seen that I can separate this product into several things. And after that, I can make the summation inside this product separate. So, okay, let's take product over all k. Now let's take sum over all delta i's in 0, 1, where I is in rk. Then we take what? Then we take product of I equals, of again I in rk ai minus delta I to the power di times k to the power sk, and maybe qk, let's take it. Actually, di are same for all numbers, yeah? Di is simply the number of bj's which are at least ai plus 1. So let's introduce new variable tk, which is number of bj's which are greater than k. Then simply tk here, tk, because they are all same. Okay, then okay, I don't have pk anymore here. Well, I have, but it is here. So times product of I in rk again, bj, not bj, but k minus delta, and also k here. Sorry. Also I have k here. K minus delta I minus k minus 1 to the power rk plus sk. No, I was wrong. I can't put it here. I can, however, write like this. Oh, so it is better than before because now I can only write it as a function of only one k. So I have a fixed k. I have a fixed k. I have several AIs which are equal to this k. And I have several BJs which are equal to this k. I don't look into other pairs of numbers or anything like this. However, I still have this ugly summation. And I want to get rid of it. Let's try to do it. Also, I again forgot about minus 1 to the power of delta. Let's write it somewhere here. So minus 1 to the sum of delta i's. Oh. Can I put it inside this? No, I cannot. Oh my god. What is qk? It's number of... Yeah, I see what it is number of. Let's at least check this formula for my favorite example 4. So it's product over k equals 4, which makes sense. Then I have sum of delta equals is from 0 to 1. So I have minus 1 to delta. Then I multiply all number. So I take... this is not taken because tk is 0. And I'm not interested. So then I have this to the power of 1. So here I have 4 to the power sk, which is 0, times product of k minus delta i's, which is simply 4 minus delta. And then I subtract 3 to the power pk plus sk, which is again 1. rk plus sk, which is 1. So this is kind of 1. Okay, this is 1. Okay, let's assume that I believe in this formula, but we need to simplify it. which shouldn't be hard, as I said. It's like symmetric. Okay, I see where it goes. Actually, I need to iterate over all possible numbers of deltas. Yeah, I have some number of chosen deltas, and I need to iterate over it. And I can do it. Okay, so product over case. Then let's assume that I chose L deltas, and I could choose them from 0 to Rk. Then I have -1 to the power L. Then I have this product, which is simply... So L is the number of chosen ones. So I have k minus 1 to the power tkl, and I have k to the power tk rk minus l. Then I have something to the power qk. Here I have k to the power sk. Then again I have this k minus 1 to the power L and k to the power Rk minus L. And then I have k minus 1 to the power Rk plus Sk. Let's continue the simplification. So again, -1 to the power L. So this cannot be simplified, which is to the left of the parentheses. But here I can make a simplification because this is k minus 1. This is simply k minus 1. No questions asked. So I can write it as k minus 1 to the power L times k to the power Rk plus Sk minus L minus k minus 1 to the power Rk plus Sk minus L to the power Qk. So this is product of all k's, then sum for all L from 0 to Rk. I forgot about choose function. I will write it right here. Choose RKL times k minus 1 to the power tk plus 1l times k to the power tk rk minus l, and finally times k to rk plus sk minus l minus k minus 1 rk plus sk minus l to the power qk. This is not the worst function in the world. I can simply calculate it in linear time, can't I? I can simply calculate it in linear time. Can't I? Well, I definitely can. It is simply what I should calculate in linear time. So I forget about anything. I forget about this. About that this should be calculated something fast. Simply do it in linear time. Yeah? Are there reasons for me not to do that? I think no. I think no. So I need the sum till Rk, and Rk is not something especially big, because Rk is the number of Aj's equal to k. Okay, let's write it. So I need some choose function. Let's make the preparations. So I need to return product of factorial n and inverse factorial of k and inverse factorial of n minus k. N minus k. Well, also, let's be... Okay, fine. Int factorial, int n, int n, and bool inverse. First of all, let's do it easy, and if n is negative, then we return 0. Then we have static vi factorials and inverse factorials, and we will return either inverse factorial of n or factorial of n. However, we cannot do it if factorial is empty. In this case, we need to recalculate all of it. I think 300,000 should be enough. Then we say that inverse factorial of n minus 1 equals inverse of factorial of n minus 1. Well, this time I'm lazy to write the function inverse for arbitrary modulus. So I will use the primality of m. So for this I need to write the function power mod. So int ans equals 1, and while b, if b and 1 ans is prod of ans am, if b divided by 2, a is prod am, then return ans. Then I need find inverse modulo m, and this is simply return power mod of a m minus 2 and m. And I really use that m is prime, but I can do it. Well, here I use false. And after that I need to fill that I fact of I minus 1 is product of I fact I m. Well, I have found the factorials. Minus 1 to the power L is also easy. So I need here to create some sort of let's do just 2 pointers. I don't see any reason to do it not 2 pointers. Like 4 int I equals, so let's just say int I equals 0, j equals 0, and while I is less than a dot size or j is less than b dot size. So let's take like so what is u? U is ai, but only if I is less than a dot size and ai is less than bj. then I take AI, else I take BJ. However, it isn't correct because here it could happen that BJ is out of the array. I could fix it by push backing like 0, but I don't want, so instead I'll say that J should be b.size or AI is at most bj. So I have this number u. Then I have to calculate these numbers. So I need to calculate rk, tk, sk, and qk. This is what I need to calculate. So rk is the number of a's which are equal to this number. So while I is less than a.size and ai equals u plus plus I plus plus rk. Then we want to calculate tk. tk is the number of bj's which are greater than k. Let's start with qk. qk is the number of bj's which are equal to k. And this can be done in the same manner. q, b, j, j, b, j, q. Yeah. Now we need to calculate the number tk, which is number of bj's which are greater than k. In t equals, so how to calculate the number of bj's which are greater than k? It's kind of simply b.size minus j. And finally, int s is the number of a's which are greater than k. And it is also easy because it is a.size minus I think. Well, we have found all of them, and then it's simply this multiplicand. So let's say that we have answer, which is 1. We return answer, and we calculate multiplicand. And answer is product of answer and multiplicand. To calculate this multiplicand, we go through L equals 0, L is at most RK. Let's think. So I need to add, so I need to like int addend, I need to calculate it, and if L is odd, then I need to subtract it from multiplicand. Else I need to add it. So now we need to only calculate this addend, starting with here. And this is straightforward. So let's start. We need to calculate choose. We have like 4 things. Okay, we have 4 things. Int thing 1, thing 2, thing 3, and thing 4. And then addend is simply the product of these 2 things. Let's calculate them separately. So thing 1, for example, is choose RKL. Thing 2 is k minus 1 to the power tk plus 1 to the power of L. So it is power mod of k minus 1, Wow, we actually have k minus 1. U minus 1 to the power tk plus 1 times L. Yeah, then k which is u to the power tk times rk minus L. So t times r minus L. Well, finally, this is harder. So this is power mod of something to the power q. And here we have difference of two power mods. What is this difference of power mods? It's power mod of k minus power mod of k minus u minus 1 actually. And what is the exponent? The exponent is r plus s minus L. Believe it or not, but we are finished. And power mod to the power q, but it is already q. Ah, yeah. Believe it or not, but we are finished. Let's see if we calculated at least something correctly. No, no. Actually, it seems like we messed with factorials. I think we messed with factorials. Yeah, we did it. Oh, now at least some of the numbers are somewhat correct. However, it seems miserable. And why is that? I wasn't really happy to see that. Okay, let's test something like this. For example, we have u equals 2. If u equals 2, let's check that everything is fine. U equals 2. So, what is r? R is the number of a's which are exactly equal to u, which is 2. This is 2, this is 3. T should be what should be t? T should be the number of numbers which are greater than k, number of b's which are greater than k. So t should be 2 and s should be 3. Yeah. Then we calculate this huge mass. And this is indeed a mess. Oh, I see. I see, it's easier. This L should have been multiplied by QK. So here I actually needed plus QK. Okay, let's fix it. I'm open to discussion. If it works, it works. Well, I love it much more. I even can submit it. Yeah, I can submit it. Let's submit it. So it should be light test, I think. And source. Well, I can actually run into tail because I think I forgot the fast input. Yeah, I forgot about the fast input. It can be simply... No, it's okay. Okay, at the worst time was like something like this. Let's speed up it. Let's speed it up with fast input. So 2, 3, 4, I think. It was this the slowest was 0, not 0.234. And here we have, of course, it's much faster. It's not 0.161 or 163. Yes, something like this. Well, thank you for watching. This was a nice problem.